Okay, talking about airfoil design today. My name is Tyrone Grantham. First question today asked to draw a symmetrical airfoil and to use arrows to diagram the negative and positive pressure points in the airfoil. So as you can see, this symmetrical airfoil here, it's pretty straightforward as it's symmetrical. You're going to have, because it's at a positive angle of attack, relative one would be this direction, you're going to have higher pressure on the top half of the wing. Lower pressure on the top half of the wing and higher on underneath. That's why those arrows, right? So arrows going to show the opposite pressure, right? So this is going to show that symmetrical airfoil. Next is the cambered airfoil. You can see the difference here because of that camber in the wing. What the pressure points is going to look like throughout that airfoil. So these are a little bit different. The pressure variations surrounding the symmetrical and the cambered airfoils have a significant impact on their lift generating capabilities. The symmetrical airfoil here produces minimal lift at zero angle of attack, but it is slightly more positive, but slightly more at positive angle of attacks because that increased pressure on the lower surface. So, however, even though it does this, their lift efficiency is lower compared to cambered airfoils. Cambered airfoils, on the other hand, with their curved upper surface, generate lift more efficiently, especially at positive angle of attack due to pressure differences between upper and lower surfaces. They're commonly used in applications requiring precise control over aerodynamic performance, so like aerobatics and stuff like that, such as aircraft. They use it in wings, and then also in turbine blades are also cambered airfoils. Cambered airfoils tend to produce more lift than symmetrical airfoils because of those capabilities we just talked about. Next here is the labeled. So a couple things we wanted labeled here. One is the camber line. So that's the line kind of through the meat of the wing, through the middle of the wing, that shows the camber that's built into that wing. The camber here is also labeled underneath. That curvature underneath the wing is that camber that's built into the airfoil. The thickness here is that widest point. It's a measurement we use to be able to measure that lift. And then that chord line, which is straight from the front to the back tip of the wing. Yep. Next, we have flaps. So first and foremost, what is a flap? What do we use them for? So flaps are going to alter the wing shape during takeoff and landing. They're going to increase lift by enhancing that camber and surface area. So it's going to increase camber and surface area, and it's crucial for low-speed flight. They're going to aid in stall prevention by adjusting our angle of attack, and they're going to be vital for safe landings. So they reduce stall speed, they allow for safer operations during takeoff and landing, and they improve control during landing because of that increased lift. This is the drawing here that I made of 4 different types of flaps. So first is plain flaps here, where that back edge of the wing is just going to basically bend down, right? It's going to move downwards. Split here is where it kind of breaks away from the bottom of that wing. So the upper surface of the wing's profile maintains the same. It's just the lower surface that changes to create that increased drag and lift. Slotted is going to be very similar to plain, but there's going to be a little tiny slot right here where it detaches. It's pretty common like a Cessna. You'll see slotted flaps on a Cessna. And then Fowler flaps here, these are going to be ones that actually extend out, kind of break away, extend out and down away from the aircraft. It allows for extreme increase in surface area, but also allows for more air to pass through these slots here, just like on the slotted flap. There's just one, but here you're going to have larger slots and multiple of them on Fowler flaps. To decrease the amount of total drag that it's creating, because the surface area is so large to create so much more lift and more control at slower airspeeds, we need to counteract how much drag is being created with those Fowler flaps. So we're going to talk today more about plain flaps. Plain flaps are going to adjust that lift and drag that we talked about. Compared to a basic airfoil, you're going to see how much longer that camber is over the top when that plain flap is extended. This is a significant enhancement in lift during takeoff and landing, but it also is a pretty notable increase in drag because they don't have any of those slots that allow that air to go through. The height and camber that it creates and the larger surface area produce additional drag forces on the aircraft. This drag is beneficial during landing approaches to help us slow down and helps us control airspeed. These plain flaps also allow us to dynamically adjust lift and drag, so we can adjust the angle that they're at, and that can optimize our performance during flight phases. During takeoff, they're used to achieve slower speeds, and during achieve flight at a lower speed, and then that's going to help us reduce your required runway length, and then during landing, going to help us slow down and decrease the amount of required runway as well too. Last, we're going to talk about winglets here. So winglets are going to offer notable aerodynamic benefits. They're going to help us to mitigate these wingtip vortices and help us reduce drag, and that's also going to help us enhance our fuel efficiency and help us with our range as well too. The winglets also increase our lift to drag ratio, enabling more efficient flight at higher speeds. So the basics here of a winglet is that you have this high pressure that's seeking to get up to the low pressure, right? It's going to create this vortice that kind of spins off the wing here. So this winglet here is going to help impede how fast and how effective that high pressure is at getting around to the wing. Without a winglet here, this would create a fast, hard vortice that would create a low pressure area that would pull the aircraft back, create more drag. Because of this winglet so high, the air has further to go and it slows down more as it moves up and around, and so it's a slower and less low pressure pulling backwards on the aircraft. This is the aircraft I fly here. You can see the winglets that extend way out. They're not nearly as vertical here like the 737, but they extend really far out, and they help decrease the amount of air they can reach around the top and create those vortices. So winglets do provide these aerodynamic advantages we've talked about, but they come with some disadvantages. They add weight and they add complexity to the aircraft, and that can be obviously increase manufacturing maintenance costs. If they're not designed properly, they can be unstable or undesirable. And so that can also affect our maneuverability. In commercial aircraft, they're going to be approved, they're going to be tested, and that's going to be, typically those will be mitigated prior to production.